once you get the cosine sum and difference identities, you can use them with the Pythagorean identity to find the sine sum and difference identities. And then once you have sine and cosine sum or difference, then you can divide them to get the tangent sum and difference identities. So once we have all of those identities to use, let's actually use them and see what happens. So something like number one, there's not much way to mess this up if you know the identity, because all you have to do is plug and chug. This is your alpha and this is your beta, or A and B in this case. And we're using the sine, and we're using the difference identity. So make sure you do sine A cosine B minus cosine A sine B, right? So sine of A times the cosine of B, and sine has the same sine, and then cosine of A times the sine of B. And our unit circle values are coming in handy here. We have the sine of 3 pi over 4 we know to be root 2 over 2. The cosine of pi over 6, we know that to be root 3 over 2. The cosine of 3 pi over 4 is negative root 2 over 2. The sine of pi over 6 is 1/2. So the first fraction multiplies together, the first pair of fractions multiplies to get root 6 over 4, right? Root 2 times root 3 is root 6, and 2 times 2 is 4. Double negative here is going to turn positive, and the top is root 2 times 1, or root 2. The bottom is 2 times 2, which is still 4. So we get the answer root 6 plus root 2 all over 4. And that's what the sign of this thing is. One thing I'd like to kind of point out here is what we really just did. The common denominator here is 12. 3 pi over 4 is the same thing as 9 pi over 12. 1 pi over 6 is the same thing as 2 pi over 12. So really what we did was we found the sine of 7 pi over 12. The problem presented itself in a way that we didn't have to think about how to break up the 7 pi over 12 into two different angles. It did that part for us, but we should start thinking about how would we start off with a 7 pi over 12 and figure out that we could write it as the difference of these two guys right here. We'll talk about that in a minute, but now we're going to move on to a degrees problem. Cosine, right? So we need to figure out an A and a B value that we could either add or subtract to get 195. Well, I don't want to do 190 plus 5 because I don't know how to deal with the cosine of 190, or the sine of 190 for that matter, or the sine or cosine of 5. I need to pick values that I like. Remember, the values that I like are from the unit circle. They're like 0 and 30 degrees and 45 degrees and 60 degrees and 90 degrees and 120 degrees and 135 degrees. And I'm starting to look at these and say, okay, I'm starting to get close to 195. I'm wondering if two numbers in this list might add together to get 195. And I'm seeing that right here, that 30 and 135. Nope, I'm not seeing that right there, am I? 60 and 135 add up to 195. So this is useful because now I can rewrite this as the cosine of 60 degrees plus 135 degrees. Okay. Again, 195 is not an angle I have memorized on the unit circle, but 60 is, and so is 135. So I can just apply the cosine sum formula here, which says cosine of the first times the cosine of the second. And then just like the sine has the same sign, the cosine flips from plus to minus, and then we'll do sine. Sine of the first times the sine of the second. And again, just like over here, these are familiar unit circle values. Cosine of 60 degrees is 1/2. Cosine of 135 degrees is negative root 2 over 2. Minus sine of 60 degrees is root 3 over 2. Sine of 135 is root 2 over 2. You're going to see some similar values that we saw over here, right? It's just in a different order. We get a negative root 2 and we get a negative root 6, but the denominators are still 4. It's a very, very similar sort of answer, and that's not uncommon for these multiples of pi over 12 slash multiples of 15 degrees, right? Pi over 12 radians is 15 degrees. So we're really just accessing all of those gaps in the unit circle between 0 and 30 and between 60 and 90, all those big jumps, right? The little jumps in the middle we've already had, but the big jumps, we're slicing those up into small jumps. All right, so maybe we can try a couple more of these before the video gets too long. Let's start off by making sure we know how to break these up, right? 11 can be made by 10 and 1, right? But I don't really much care for 1/12. I don't want to deal with that. 11 can also be made using 9 and 2, right? We can add these guys up. But notice that 9 over 12 reduces to 3/4 and 2 over 12 reduces to 1/6. So we could actually use the same 9 pi over 12 and 2 pi over 12 that I used up here, down here, just by changing the minus to a plus. Okay, I'm not going to do that because I want some variety here, and I want to point out that, well, this one's not very useful. This one works, but there's some other ones that work. I could also try 8 over 12 plus 3 over 12, right? Because 8 plus 3 equals 11. And these guys reduce as well. So I'm going to use this. I'm going to say that the sine of 11 pi over 12 is equal to the sine of, this reduces to 2/3, so 2 pi over 3, plus this reduces to 1/4, so pi over 4. Again, it's not wrong to use these guys instead. Just toss a pi in front of them, right? And reduce them. But just for the sake of giving you another idea of how we can do this, this is another way we could. And we could keep on going, right? 7 plus 4 is going to give us 11, but 7 over 12 doesn't reduce. So I don't really like this one. I don't really like this one. I want to make sure I'm picking ones that actually reduce. So find ones that reduce and then use those. All right, so let's go ahead and try this one as well. Again, 5 pi over 12. Maybe I'll use subtraction this time. I could do 6 over 12 minus 1 over 12, or, well, that doesn't help because that doesn't reduce. I could try 7 over 12 minus 2 over 12. That doesn't work because 7 over 12 doesn't reduce. I don't like either of those. But what about 8 over 12 minus 3 over 12? Oh, wait a second. That's the same things we had over here, right? So we could actually just go ahead and use, whoops, don't leave out this. We're still taking the cosine of it. And 8 over 12 reduces to 2 over 3 still. And 3 over 12 still reduces to 1 over 4. So the changes on this are that I use a plus here and a minus here. So sum formula versus difference formula. And also, obviously, it's a sine problem over here and a cosine problem here. But that's just picking which identity to use. Now, some of you are going to say, well, that's too hard. Subtraction is messy, and why don't we just use adding? And yeah, we definitely can use 2 over 12 plus 3 over 12, or 1/6 plus 1/4, or pi sixths plus pi fourths. And that's 100% fine. It's going to give you the same answer. Play around with it and see what happens. Okay, so there's no one right way to do these. You kind of have a choice. And then back to degrees here. Go back to that list that we were looking at here. How to get 165. Well, that's what I tried to do before, then I corrected myself. 30 plus 135 would work, right? So I can do the tangent of 30 degrees plus 135 degrees. And there are others, right? So you might find a different one. Either way. And then 15 is kind of the smallest one, right? It's kind of halfway in between 0 and 30. So I don't think we can add very easily to get these, but we could definitely subtract, right? Maybe 45 minus 30. So tangent of 15 degrees is the same thing as tangent of 45 degrees minus 30 degrees. So that's kind of a nice first step for all 4 of these problems, okay? Figure out how to break it up and then apply the identity. Okay, since we've already done a sine problem, we've already done a cosine problem, maybe I'll finish up this video by doing a tangent problem. I'll do the tangent of 165. So the tangent sum formula tells you, well, you can either find the sine and the cosine, or we can do this tan A, this is plus that we're dealing with, so tan A plus tan B in the numerator, and 1 minus tan A tan B on the bottom, right? So if we're using the plus, which we are because of that plus right there, then use the top sign. So the top sign here is plus, the top sign here is minus. So tan plus tan over 1 minus tan tan. Okay? So when we apply that, let me zoom in on this so it's not quite so teeny tiny. When we apply that, we get the fraction in the numerator. We get tan plus tan, so tan 30 degrees plus tan 135 degrees on the top, and then 1 minus tan tan on the bottom. It's like a dance. Isn't the tan tan a dance? Or is it the can can? I think it's the can can, actually. Anyway, we know how to deal with tangent of 30 degrees. That's root 3 over 3. We know how to deal with tangent of 135. That's negative 1. And then we see the same values down here, minus root 3 over 3 times negative 1. Okay. Now this is kind of a messy answer, so let's see some things we can do to clean it up. For example, plus and negative is the same as minus. And negative times negative is the same thing as a plus. Now, I don't like fractions inside fractions. We can find common denominators on the top and also on the bottom, but I tell you what, the easiest way to reduce this, get rid of the fractions inside fractions, is just multiply the numerator and the denominator by that least common denominator of 3. Just make sure you distribute it to everything. 3 over 3 is 1, so we're allowed to do that. And we get root 3 over 3 times 3 is root 3. 1 times 3 is 3. And then on the bottom, we get 3 plus root 3. So that's a much nicer answer, but it's still not considered simplified because we've got square roots in the bottom. So you might think, oh, now I'll just multiply by root 3 on the top and the bottom. But we know that doesn't work, right? Because if we try that when we distribute, yeah, that'll get rid of that square root, but it'll introduce a new square root over here. So we can't do that. What do we do instead? That C word, right? Conjugates. So whatever the denominator is, multiply by its conjugate. And if we multiply the bottom by the conjugate, we better multiply the top by the conjugate, right? That orange fraction, just like this orange fraction, equals 1. So we're allowed to multiply by that orange fraction. So now we have to distribute out, right? Root 3 times 3 is 3 root 3. Root 3 times negative root 3 is negative 3. Negative 3 times 3 is negative 9. And then negative 3 times negative root 3 is positive 3 root 3. Okay. The radicals don't cancel out on the top. We didn't really expect them to. They have to cancel out on the bottom. Remember the conjugates, a plus b times a minus b, gives you a squared minus b squared, right? The outer and the inner, when you distribute, are going to cancel out. So that's going to give us a rationalized denominator, and we'll combine like terms in the numerator. So positive 3 root 3 plus 3 root 3 is 6 root 3. Negative 3 minus 9 is negative 12. On the bottom, we've got 9 minus 3, or 6. So when we divide 6 root 3 by 6, we get root 3. And when we divide 12 by 6, we get... Pay no attention to the bell. We get 3 root 2. And that would be your nice final, simplified, rationalized answer.